So with your green packet out, open to derivatives, these are all of the individual objectives. Take a look at those and see what you know, or what I should say you should know at this moment, and then what we have yet to do. Okay, so first things first, what's the first thing on the list that we have not done yet? Implicit differentiation, and then see that's what we're going to do today. Okay, then you see after that we only got a couple things to go. E to the x and e to the u, and then natural log of x and natural log of u, and then a combination, putting all of them together in any combination that we can and being able to solve a problem. All right, is there anything prior to that list that needs just a brief explanation? Because I know we did each of those. Anybody recall anything?
What's the difference between slope and rate of change?
Slope and rate of change. Slope is when you just consider rise over run, and there are no units. Okay. In rate of change, it means that the x and the y axes have different units. So it might be miles here, and it might be hour here. So the slope actually has a unit, and it's miles per hour. That's the difference. So when we say rate of change, it means always that it's comparing two things. It's the same exact thing as a slope, where you consider rise over run, but it's actually a unit of measure, where slope doesn't have one. Okay. Anything else on that list that you do not know or do not recognize? How you doing, Libby? Yeah.
The constant rule is just like if there's any equation y equals like 5.
Correct.
Then it'll always be 0.
Right. So the difference, I want to point that out, the difference between the constant rule and the constant multiple rule is the derivative of a constant. Now notice my notation here. The derivative with respect to x of some constant is equal to 0. Okay? That means that the function, remember the thing that goes in here is the actual function that we're finding the derivative of. And here it's the derivative of a constant, which is 0. The constant multiple rule looks like this. I'll use k this time. It says, what's the derivative of a constant times a function? Some constant, some number. And it's equal to the constant times the derivative of the function. Okay, or in other words, it's k times f prime of x. Okay, so constant rule, constant multiple rule is what we have there. This is what allows you to pull out the constant when you're finding the derivative of a function. Okay? Yes?
The difference, or explain the relationship between differentiability and continuity.
Sure. Differentiability implies continuity, which means that if you know that a function is differentiable at a point, then you know automatically that it's continuous at that point, but not the other way around. Just because a function is continuous at a point does not mean that it is differentiable at that point. And we said a cusp is the perfect example of that. A function is not differentiable at a cusp. Also, I think we saw this the last time we were together. Remember we had a vertical tangent? Okay, vertical tangent. That meant that the function was continuous at that point, but its slope was, a slope of the line tangent was vertical, which means that it was undefined, which we would say that it's not differentiable at that point.
So great.
Okay. What happened? Got sucked into the Packers sign. Okay. So take out your. So then now you can set this aside. You can see where we're going. Yep.
I know we probably went over, but I don't remember the 6 basic trigonometric derivatives.
Okay. Let's just do them quick. The derivative of the sine function, cosine. Derivative of the cosine, negative sine. Derivative of the tangent, secant squared. The derivative of the secant, they're in your book. Just use the quotient rule to compute each one of those. Now, this reminds me of the fact that we will have our exam on the Friday before Thanksgiving. Okay, before Thanksgiving, which means we will have, we will also have that week prior to it to do the practice the exams like we did the last time. Okay, so we have that, and that means that your chapter summaries for all of these sections is due on that Friday. So every one of these sections that's here, your chapter summary. You did it. So, and I would highly recommend that you do those now. You might even find that they'll be useful to do that now.
I'll get done.
Just. All right, take out your notebook and take this down. We are moving on today. Is that the Friday before? Yeah. The 20th, November 20th is our test. Yes, question? Yes? It is?
Oh, yeah.
All right. Well, then you guys will take it before that. No, we'll figure something out. You would know.
So I'm not.
Okay. So today's lesson, we're going to spend probably 3 days on this so that you understand all of the details that go along with it. This is a big topic. There's questions on the exam that have to do with this, and it's called implicit differentiation. So what does that mean? Well, our goal in this is to find the derivative of any relation, okay, which is now a different question than when I said our goal was to find the derivative of any function. Okay, and let me explain what that means. So any set of ordered pairs, if it has x, y's in it, if it's a set of ordered pairs, it is a relation. Okay, any set of ordered pairs like that is a relation. But only a subset of relations are actually functions. Okay, we have the excuse me. We have function mode on our calculator, and it always starts off as y equals. Okay, so anything that can be written as y equals is a function. Okay. However, there's coordinate pairs that form pictures that are not functions. For example, x squared plus y squared equals 100 is the one that's going right now. That's a circle, okay, centered at the origin. This one's with a radius of 10, and it's an infinite number of points that where every point on that graph satisfies this equation. But it's not a function. Okay? Doesn't pass the vertical line test. Okay? So what we're going to do in this whole thing is, watch this disappear, is we're going to look at different functions, different relations, see what kinds of things are out there, and then we're going to find the derivatives of them. Hit that first light, yeah. So this is an easy one, so I'm going to take that one off. But what if you did x cubed plus y cubed? So this is x cubed plus y cubed. And then you say, okay, well, what if we did x to the fourth plus y to the fourth? So now it's no longer a circle, it's like this square. Okay?
Mr. Johnson, is there any way you could make it so that A is always a positive, but it's going to keep disappearing?
Well, that's actually good to know. Why does it disappear?
Because they're even exponents.
You can't ever get a negative here. Okay, so, but on the negative ones, okay, watch what happens here. Okay, if you take it just to the positives, you have that. So that's that. Well, and if we did x squared minus y squared, and then if you did x squared minus y to the third,
What is this?
and then if you did x cubed minus y cubed, you get that one. That goes the other way.
Oh,
Now, this is the fun part about this. Every single dot that creates this picture has an x and a y coordinate, and if you plug in the x and the y, it satisfies this equation, where a divided by x squared minus a divided by y squared is equal to x times y. The complete solution of all of the x's and the y's makes this picture. That's, in essence, what a graph is.
oh.
So that's kind of interesting. Yeah, I just sit here and play. When you guys are gone, this is all I do.
This is interesting. There's no A.
This one has
Oh, there's no
It's
A.
just 7.
Oh, yeah. Watch this. Something really funky happened right above us.
Oh, no.
Yeah. I'm gonna just manually do this one, actually. Watch. This is so cool.
Oh.
It separates.
Oh.
Isn't that horrible?
It's so cute.
This is a relation. Okay? It's not a function. Obviously, it fails the vertical line test. But that's what's going on there. And then we've got another one. So if you want to know what the infinity symbol is, it actually has a graph. Okay, this one's tilted, so this one's not. This is the graph of the infinity symbol is a relation which can be defined with an equation. Isn't that cool? With different x and y values.
Oh.
So you can see I'm using funky exponents there of 2/3. So
Forever. I really don't think it's
I could.
No, I like that.
Oh no.
That has not been fully resolved.
yeah.
Okay.
So each of these.
Are we getting it? I know. Thing. I was like, if you
Memorize all those, right?
Yeah, you have to memorize all of these.
Okay, good.
what is that?
No.
For me, it's so exciting.
So this one,
This is what like fashion designers do.
this is a graph. This is a graph,
Oh.
okay?
So pretty.
And the graph is this equation: the sine of x plus the cosine of 2y is equal to a. And every point on this satisfies the equation. Isn't that cool?
You could do something really cool with like multiple colors and like make
So
Yeah, put off.
if I decided,
Yes.
Keep going. It's literally blowing my mind right now.
look at how they are connected here.
Oh.
Oh my goodness.
Oh my.
abstract.
Ah, yeah.
Yeah.
Oh my goodness. What's that last one though? Yeah.
I don't know why I have
That
this
was
one.
just like a parabola. It's not interesting.
Okay. So
Whoa.
all right. So now okay, look at this, how that all matches up.
You get rid of the purple box and look like first wearing glasses.
But it looks like a smiley face. It looks like a smiley face, so if you ignore the compact blue, it's correct Spider-Man.
Okay, so I should put a parabola down here,
Yes.
right?
Give her the purple box.
And then give them some eyebrows,
Let's grab a person.
and then have some people come up here, give them ears.
I challenge you to graph a person right now.
If you go on Desmos, you will see that there are there's a ton of example graphs where people have made some crazy things that you're like, how did they actually do that? It's like it looks impossible. We are not going to look for them in class because that we could spend the entire day on that. Okay. All right, so here's the golden question. How do you find the derivative of something that is no longer a function? Something that is crazy like some of the stuff that we just saw. By the time we finish here, you're going to be able to find the derivative of any one of those things, which means we can find the slope of the line tangent to any one of those curves at any given x and y value. Okay? That's the goal of implicit differentiation. Okay, some stuff to know before we actually do this. Okay, so first thing, implicit versus explicit is the first thing, because it says implicit differentiation. So what does that mean? Well, if I write a function explicitly, that's something like this. Okay? Those two functions, and we could write lots of them, are written explicitly. That means they're solved for y. Okay? To have something implicit means that the y is actually embedded in the problem. Okay? So, meaning if I had something like x squared plus y squared equals 100, that circle, this is an implicit equation because the y is embedded inside of it. We didn't solve it for y. Okay, so anything where we have, the cosine of y minus the sine of x is equal to 7. Okay, this is written implicitly.
If you solved it for x, would it still be explicit? Be explicit about the x.
Yeah, that's a good. I've never had that question asked. I say that we say these are explicitly solved for y. So you could solve it the other way, be explicitly solved for x. So when you see this, make sure that you have that. Now watch this. This is actually written implicitly. You see that? Because it's not solved for y. It's xy is equal to 4. However, I could write this as y equals 4 over x, and now I took the same exact thing, same exact equation, and now I wrote it explicitly by solving for y. Okay?
Which is how it's written.
How it's written. The difference is that this is a function. Okay? It's a function. These two are not functions. Okay? You can't solve them for y and graph the whole thing. You can't punch it into your calculator in function mode. Okay? Your kids will have implicit mode on their calculators. And so they'll be doing stuff like this on their calculators. We don't have that ability except for a graphing calculator like this. And there is a Desmos app, by the way. If you want to just play with it, it's a lot of fun.
Desmos on the go.
Desmos on the go. Question? Okay. The second thing is what is the derivative of y? Okay. When we do this, the question is what is the derivative of y? Well, we're going to start off with only x's and y's. So what we think of this as is that y is actually dependent on x. That y is in itself a function of x. So we're going to actually incorporate a chain rule idea here. What I'm really asking for is, what is this? What is this equal to? What is the derivative of y whenever we come across it in these problems? And the answer is that it's equal to dy dx. So whenever you see us finding the derivative of y, we're actually going to be finding dy dx. Okay. A third thing is that you have to remember the chain rule. Okay. Because we're going to treat this whole y thing as a chain rule. Okay. All right, so let's start off with some examples. So I'm going to try to start small. Okay. So first one, what is the derivative of x squared? Answer? 2x. We are quite familiar with that. Okay? And this is the notation. This means find the derivative of this thing, this function, with respect to x. All right, but now watch this. What is the derivative of y squared? What is the derivative of y squared? The natural thought is 2y, right? But it's incomplete. It's 2y multiplied by the derivative of y, which is dy dx. That's where the chain rule comes in. Okay? Now, let me try to explain this. Technically, okay, now watch this. Watch how I'm going to write this. D dx of, watch this, x squared. Look at how I'm writing this. Okay? This is the same as this. But I'm writing it because I'm going to emphasize the chain rule here. What is the derivative of x squared? And I'm going to apply the chain rule here. Watch. This is something squared. So the derivative of something squared is 2 times the something raised to the first power, multiplied by the derivative of what's inside with respect to x. What's the derivative of x with respect to x? 1. That's why the answer is 2x. We've actually been doing the chain rule all along. Because if we think of this as something squared, then the derivative is 2 times the something to the first power times the derivative of the something, and so, but the derivative was always 1. Make sense? Okay. Now, let's take a look at this. I'm going to rewrite it just like I did the other one. So I'm going to say d dx of u squared. And watch the connection. What?
You said u squared.
I said u squared? Okay. It's supposed to be y. Okay, in my brain, I'm thinking of, I already did the substitution, y is equal to u. Okay, so what is the derivative with respect to x of something squared? Using the chain rule. Well, it's 2 times the something to the first power multiplied by the derivative of what's inside. And what did we say the derivative of y was? Dy dx. That's why the answer is 2y dy dx. Okay? Yes?
I'm kind of confused on what a dy. I know that we solved the dy dx earlier, but I'm kind of confused on where that
dy dx represents the derivative of y. And so, in here in the chain rule, when we reach the moment where we had to take the derivative of the y, the answer is dy dx.
Will we be substituting something in for that later, or is that like the final?
That's the final answer. So the derivative of y squared has 2y, is 2y dy dx. Now that's weird, because all the way up to this point, we always said dy dx equals. Okay? So watch the connection here. Coming. Okay. So watch the connection. In the past, I've said to you things like, oh, find me the derivative of this. And then, so you may have gotten almost to the point where you've forgotten where things have come from. Watch this. If I'm going to find the derivative of this, what I'm going to do is actually find the derivative of both sides. Just like we've done things in the past in algebra class. Oh, well, let's square both sides, or let's take the square root of both sides. So with the original one here, if I find the derivative of both sides, then the derivative of y with respect to x, that's where that symbol comes from, dy dx. It represents the derivative. And then whatever the answer is on the right side is what the derivative is. Okay? This is what we've done in the past, and this was all functions. Okay? Our problem now is that these are not explicitly solved for y. The y is implicitly involved in the equation, so that means that anytime we do these, the answer, the dy dx, is actually part of the problem. Okay? All right. Let's take a different one. Let's say x squared plus y squared equals 100, like I had here. Everybody recognizes that as a circle with a radius of 10, centered at the origin. So if I want to know the slope of the line tangent at any point on this circle, I need to find the derivative of this. So this is how we do it. I'm going to follow the same technique here. Watch what I'm going to do. I'm going to find, I guess I'll just write the whole thing out. I'm going to find the derivative of the left side, and I'm going to set it equal to the derivative of the right side. So if you have an implicit equation and you want to find the derivative of it, you find the derivative of both sides. And then watch what happens. The derivative of x squared plus y squared. Okay. Well, lo and behold, look at that. We already did those two. So the derivative of the first one. So what's the derivative of x squared? 2x. What's the derivative of y squared? 2y multiplied by dy dx is equal to 0. What we've just done is we've found the derivative of both sides. And now, does it make sense that if the y was embedded into the original equation somewhere, that the dy dx is going to be embedded into the equation somewhere? And then all we have to do is we just solve for dy dx. And that's our derivative. So watch. dy dx. So this is going to be 2y times dy dx is equal to negative 2x. And therefore, dy dx is equal to negative 2x over 2y. Therefore, if you want to find the slope of the line tangent to a circle at any given time, all you have to do is take the x-coordinate, divide it by the y-coordinate, take the opposite of that, and that's the slope of the line tangent to the circle. Believe me? Let's just test that. So we'll just draw a quick picture and see if it makes any sense. And what's fun about this is that derivative is the same no matter what the radius is, because the derivative of the other side is 0. Okay? So we're going to test this by considering a circle with a radius of 5. 5 units. So I draw a circle, and it's got a radius of 5. I picked 5 because it's going to have easy numbers for us to work with. Okay. So I'm going to pick a point here. 1, 2, 3, 4. At 4, my coordinates are 4, 3. 3 squared plus 4 squared equals 5 squared. It's a Pythagorean triple. Okay, so boom, boom, 3, 4, 5. Okay. Now, according to this formula, what is the slope of the line tangent at this point? So I draw the slope right here. What is the slope? Negative 4 over 3, according to that. That's the slope of that line. What's cool is there's actually 2 points when x is 4, and my circle is really bad here. Here's my circle. Okay. So right here, isn't this also a place where the slope, where x is 4? What's the slope at this point? It's positive 4/3. So look at this. What's unique about this equation compared to all of the ones we've done in the past? What's unique about this derivative? Come on, come on, come on. You what? Not just 2 points. It contains not just x's, but it contains x's and y's. Which means because this handles the situation of it failing the vertical line test and having multiple points. X is 4 here, x is 4 here, but the 3's are opposite, and we can still find the slope at this point and at that point because we have to plug in both the x and the y into an implicit derivative. Okay, this was day 1. We're going to look at this tomorrow and the next day. Okay, so let's make this assignment here, page 146, due Friday. Due Friday. Page 146, due Friday.